Imagine a world where calculations that would take the universe's fastest supercomputers billions of years are completed in mere minutes. That world is closer than you think thanks to Google's latest quantum computing breakthrough. Meet Willow, a quantum chip so advanced it's rewriting the rules of computing and unlocking new frontiers in science, technology, and even our understanding of reality itself. Google has unveiled Willow, its fourth-generation quantum chip, marking a monumental leap in the field of quantum computing. What makes Willow extraordinary isn't just its advanced architecture, but its jaw-dropping capabilities. This chip recently completed a computation in just 5 minutes, a task so complex that even the most advanced supercomputer would need 10 septillion years to achieve it. At the heart of Willow's power lies its 105 qubits, the building blocks of quantum computation. Unlike classical bits, which exist as either a 0 or 1, qubits operate in superpositions, allowing them to perform multiple calculations simultaneously. This unprecedented level of parallelism enables Willow to tackle problems far beyond the scope of classical computing, from solving intractable equations to simulating quantum phenomena. This isn't just a step forward, it's a quantum leap into a future of infinite possibilities. Quantum computing, despite its groundbreaking potential, faces a fundamental challenge: quantum error correction. Unlike classical computers where errors are rare and predictable, quantum systems are highly sensitive to even the slightest environmental disturbances. These errors can quickly cascade, jeopardizing the accuracy and reliability of computations. Overcoming this hurdle has been one of the biggest bottlenecks in advancing practical quantum technologies, until now. Google's Willow chip introduces a game-changing approach to quantum error correction. By achieving what's known as a below-threshold performance, Willow demonstrates exponential error reduction as the system scales. This concept hinges on the idea that once the error rate per qubit drops below a certain threshold, adding more qubits to the system reduces the overall error rate exponentially, rather than amplifying it. This is a major milestone as it provides a path to building large-scale, fault-tolerant quantum systems. Willow's advanced design incorporates real-time error correction mechanisms that constantly monitor and correct for quantum state fluctuations. These corrections are applied almost instantaneously, ensuring that computations remain accurate even in the presence of noise and interference. For instance, the chip uses logical qubits, virtual constructs formed from multiple physical qubits, to detect and correct errors without disrupting the delicate quantum states. The implications are profound. Real-time error correction doesn't just make the system more reliable, it also dramatically enhances its computational accuracy. For complex tasks, such as simulating quantum materials or solving optimization problems, maintaining error-free states is critical. Willow's ability to dynamically manage errors represents a leap forward in quantum computing's journey from experimental novelty to practical application. By addressing one of the most significant technical barriers in quantum computing, Willow is setting the stage for a new era of precision and scalability. This breakthrough brings us closer to unlocking the full potential of quantum systems, where error-free computations can tackle problems once thought unsolvable. In the evolving landscape of quantum computing, the random circuit sampling, RCS, benchmark stands out as a pivotal test. This benchmark evaluates a quantum computer's ability to simulate highly complex random quantum circuits that are virtually impossible for classical supercomputers to compute. It's a rigorous measure of a system's speed, accuracy, and overall capability. Google's Willow chip has not only risen to this challenge but has set an extraordinary new standard in the field. Willow's record-breaking achievement in the RCS benchmark highlights its ability to solve problems that classical supercomputers would find insurmountable. By executing a computation in a matter of minutes, one that would take Frontier, one of the world's most advanced supercomputers, several years, Willow has demonstrated its quantum supremacy. Frontier, housed at the Oak Ridge National Laboratory, represents the pinnacle of classical computing power. Yet, Willow's performance underscores a transformative moment, the clear and tangible advantage of quantum processors for specific computational tasks. What makes Willow's RCS performance exceptional is its unprecedented scale and precision. It processed circuits with 105 qubits, achieving results that confirm the system's stability and error resilience. Classical computers, even with the aid of sophisticated algorithms and massive parallelization, cannot handle the sheer complexity of these quantum circuits. The exponential growth in required classical resources makes such tasks computationally prohibitive. The implications of this achievement are profound. First, it validates the potential of quantum computers to tackle real-world problems in areas like cryptography, optimization, and material science, where traditional systems falter. Second, it signals a significant leap in quantum error correction, a critical factor in maintaining the reliability of quantum computations over extended periods. Finally, surpassing frontier, a symbol of classical computing's zenith, marks a historic turning point, heralding a future where quantum systems take center stage. Willow's performance in the RCS benchmark not only advances the boundaries of what quantum technology can achieve, but also accelerates the timeline for its practical application. The era of quantum computing is no longer theoretical. It's unfolding before our eyes, with Willow leading the charge into uncharted computational territories. The groundbreaking achievements of Willow are reshaping the future of quantum computing, bringing us closer to solving complex problems that were once thought insurmountable. As quantum technology continues to evolve, staying informed about these advancements is crucial for anyone invested in the future of computing, AI, and technology. If you want to dive deeper into the world of quantum computing and explore how innovations like Willow are changing the game, make sure to subscribe to my YouTube channel, Trend AI Tech. Get access to insightful videos and stay ahead of the curve on the latest breakthroughs in AI and quantum computing. The concept of quantum computing often seems like something out of science fiction, and according to Hartmut Neven, Google's director of quantum artificial intelligence, this perception might not be far from reality. Neven has suggested that quantum computation could be taking place in parallel universes, a provocative idea rooted in the multiverse interpretation of quantum mechanics. This theory not only challenges traditional perspectives, but also opens doors to a reimagined understanding of computation and existence itself. To unpack this, let's first explore the multiverse theory in the context of quantum mechanics. According to this interpretation, every quantum event results in the universe branching into multiple parallel realities, each corresponding to a different possible outcome of that event. For example, when a quantum bit or qubit exists in a superposition, representing both 0 and 1 simultaneously, the computation effectively occurs across multiple states or realities. This phenomenon becomes even more pronounced when dealing with the vast number of qubits in a quantum processor like Willow. Neven's suggestion builds on this idea. He postulates that quantum processors leverage these parallel universes to perform calculations. Instead of relying on classical computational steps, linear and sequential, quantum systems exploit the intertwined probabilities of countless states. This process could be likened to accessing computational power from alternate realities, where each parallel universe contributes a small piece of the overall solution. While this concept is still speculative, its implications are profound. It challenges the classical notion of computation, which is confined to a single deterministic reality. If quantum computing indeed draws on resources from parallel universes, it could redefine the limits of what's computationally possible. Problems once deemed unsolvable due to their complexity could become tractable, as quantum computers sidestep the constraints of traditional binary logic. Moreover, this idea invites a surge of interdisciplinary research. Physicists, computer scientists, and philosophers alike are compelled to reconsider the nature of reality, computation, and consciousness. If parallel universes exist and quantum computers interact with them, what does this mean for our understanding of time, causality, and the fabric of existence itself? The multiverse theory is undeniably speculative, but its association with quantum computing underscores the field's transformative potential. As researchers continue to explore these possibilities, one thing is clear: quantum computing is not just advancing technology, it's reshaping our fundamental understanding of the universe. Whether Neven's hypothesis holds or not, it points to the vast, untapped horizons awaiting discovery in this quantum revolution. Quantum computing has long been heralded as a game-changer for solving some of the most pressing challenges humanity faces. With Willow, Google's fourth-generation quantum chip, we're beginning to see the bridge between theoretical breakthroughs and tangible, real-world applications. The potential impact spans industries as diverse as climate modeling, drug discovery, artificial intelligence, and more. Tackling climate change. One of the most promising applications of quantum computing lies in climate modeling. Traditional supercomputers struggle with the sheer complexity of simulating global climate systems, which involve countless variables interacting over vast timescales. Willow's ability to process immense datasets exponentially faster opens the door to more accurate predictions. These insights could guide policymakers and scientists in designing effective strategies for mitigating climate change, from optimizing renewable energy grids to forecasting extreme weather events with unprecedented precision. Accelerating drug discovery. Drug discovery is another field poised for transformation. Identifying effective treatments often requires simulating molecular interactions, a process that is computationally intensive and time-consuming with classical methods. Quantum computers like Willow can model these interactions at the quantum level, drastically reducing the time and cost required to bring new drugs to market. This capability is particularly relevant for tackling diseases that have eluded effective treatment, such as cancer or neurodegenerative disorders. Advancing artificial intelligence. Quantum computing also has the potential to revolutionize artificial intelligence. Many AI processes, such as training large neural networks or optimizing algorithms, are computationally expensive and slow. Willow's capacity to handle vast and complex calculations efficiently can accelerate these processes, enabling breakthroughs in machine learning and deep learning. Quantum-enhanced AI could lead to more accurate predictive models, improved natural language processing, and smarter decision-making systems across industries. Bridging theory and practice. While the applications are exciting, Willow's true contribution lies in making commercially relevant quantum computing a reality. Historically, quantum computers have excelled in theoretical benchmarks but struggled with practical, real-world problems. Willow changes this narrative by demonstrating exponential error reduction and scalable quantum error correction, two critical advancements that move us closer to reliable, large-scale quantum systems. Moreover, Willow's success in achieving below-threshold error correction and its record-breaking performance on the random circuit sampling benchmark are not just scientific milestones, they are stepping stones toward practical algorithms. These algorithms could be deployed in real-world settings, solving problems that classical computers can't address within feasible timeframes. Shaping the future. As quantum technology evolves, Willow represents a critical juncture in the journey toward unlocking its full potential. By bridging the gap between abstract quantum mechanics and practical applications, Willow sets the stage for a future where quantum computing becomes an indispensable tool in industries ranging from healthcare to energy, finance, and beyond. The promise of solving humanity's most complex problems is no longer a distant dream, but a tangible possibility, one that Willow is bringing ever closer to reality. Willow, Google's fourth-generation quantum chip, marks a pivotal moment in the evolution of quantum computing. By addressing critical challenges like quantum error correction and breaking new performance records, Willow brings us closer to realizing the true potential of quantum technology. Its achievements in random circuit sampling and real-time error correction pave the way for practical applications that can revolutionize industries such as climate science, drug discovery, and artificial intelligence. As quantum computing continues to mature, Willow stands as a beacon of progress, bridging the gap between theory and real-world solutions. The future of quantum computing is no longer a distant vision, it's a reality in the making, with Willow leading the charge.